Hello guys, welcome to our YouTube channel. In this video we will be designing a voltage divider biasing scheme for the MOSFET. The specification for the design follows as VDD is 1.8 volt and drain resistance is 500 ohm and drain current is 1 milliampere and W by L aspect ratio of the MOSFET is 20 by 0.18 and the required input impedance is 20 kilo ohm and threshold voltage of the MOSFET is 0.4 volt and nuance oxide, a process parameter, is 200 microampere by volt square. Initially we will name this node as Vx and drain node as Vd. Then we have to apply KVL to the input loop. Then we will get Vx is equal to Vgs. Vgs is the voltage difference between gate to source. Then Vx can be found from the voltage divider formula as VDT into R2 divided by R1 plus R2. We have to ensure that the MOSFET is in the saturation region and the drain current required is 1 milliampere. Then we have ID is equal to 1 by 2 into nuance oxide W by L into Vgs minus Vdh whole square. Here we have to apply all the given values, that is 1 milli of drain current. To nuance oxide is given as 200 micro, then W by L ratio is given 20 by 0.18, then VGS is we have to find, then we will substitute as Vx only, then Vth is given as 0.4 volt then square. Here we will get Vx as 0.7 volt. For MOSFET in saturation, we have to ensure that Vd should be greater than Vg minus Vth. So we have to find Vd values that can be found from applying KVL to the output loop, that is VDD into ID RD minus VDS equal to 0. VDD is 1.8 volt, ID is 1 milliampere, RD is given as 500 ohm, then VDS as it is, then we will get VDS as 1.3 volt. So we can tell that the MOSFET is in saturation because VDS is greater than Vg minus Vth. After finding the voltage at the gate and drain node of an MOSFET, we have to apply the Thevenin's theorem to our circuit at the input side. In Thevenin's theorem, any linear circuit can be modeled as a single voltage followed by a Thevenin's resistance. Then we can break this circuit into two halves, that is, one is input side and one more is output side. Here we have to apply the Thevenin's circuit to the input side. Then we can replace this input side configuration into a single voltage source Vth followed by an Thevenin's resistance Rth. Then output side is still same because we applied Thevenin's theorem at only input side. So output side is unaltered VDD. To find the Thevenin's voltage, we have to find the node at which we applied the Thevenin's theorem. That the node at which we applied Thevenin's theorem is Vx, so Vth is nothing but Vx. That is how we find the Thevenin's voltage. Vx is equal to VDD into R2 divided by R1 plus R2. To find Rth, we have to short all the voltage sources and open circuit all the current sources. Then when we short the VDD, then this R1 falls in parallel with R2, so Rth is given by R1 parallel combination of R1 and R2. Then we have Rth is equal to R1 into R2 divided by R1 plus R2. And also from the specification of the design, it is stated that the input impedance should be 20 kilo ohm. From the Thevenin's circuit, we can tell that the input impedance Zin is nothing but the Thevenin's resistance RTh. So we can write Zin equal to RTh equal to 20 kilo ohm. So R1 into R2 divided by R1 plus R2 is equal to 20 kilo ohm. Also from the Thevenin's voltage, we have VTh is equal to Vx is equal to 0.7 volt. This the 0.7 volt is obtained in the previous step. Then we can write VDD into R2 divided by R1 plus R2 equal to 0.7 volt. Then R2 by R1 plus R2 can be written as 0.7 divided by VDD, that is 1.8 volt. This fraction comes around 0.389. Then we have to write, then we know that R2 by R1 plus R2 equal to 0.389. then we can replace this value as 0.389. R1 0.389 equal to 20 kilo ohm. Then R1 is equal to 20 kilo divided by 0.389. then R1 comes around 51.414 kilo ohm. And we can also find R2 substituting R1 as 51.414 kilo ohm in the equation. In this equation we will get R2 as 32.73 kilo ohm. These are the values of R1 and R2 for our circuit for the given specification. Thanks for watching.